Okay, so good evening, everyone. So we have now week 9. So week 9 today we have to plan to discuss the week 9 content, and this is also very important for your OPP exam. Okay, so one question definitely will come from this dynamic programming concept. So we will discuss the content of week 9, and this Friday we will discuss the problem based on the dynamic programming, and also this week and the coming week. So all tier revision sessions will be based on the OPP actually. Okay, so we have divided the topics, and based on that topic, TA will actually discuss some problems on all session till OPP exam. Okay, until the first date of the OPP exam. Okay, so attend all the live session, that TA revision session. Next week we will also try to conduct two session that is for revision like session. Okay, so one is definitely we will release mock. So we will discuss mock problems also, and we will discuss some important things. Ajay, I have also mentioned on the discourse what topics are important. So first one question for linked list you can practice. Okay, one question from the graph algorithms, one question from DP, and one question maybe from different topics like binary search tree, VD algorithm, any like sorting algorithms. Okay, so these are the like distribution of the problems you can practice accordingly. So, okay, so now quiz 2 have done. How was the quiz 2 exam? We got this time good result overall in the quiz 2 exam. So, but according to you, how was the exam? It was difficult or moderate? Any comment on this?
Sir, moderate.
Moderate, not difficult. Okay. Yeah, any other, if you want to share your experience with quiz 2, how you feel that? Okay, no one want. Okay. Overall result is good compared to the previous term this time. So yeah, we will check also if any question. If you have any doubt in any question, you can post on the Discord. So we will also check. Okay. So at the time of finalize of the result. So okay, fine. So let's move to the week 9 contents. This is dynamic programming, very important topics for the future competitive problems also. Okay, so that is very advanced programming topic. So if you want to move into the competitive programming platform, so that is a very important topic for that. So let me share my screen, and we will discuss the content of week 9, and we'll also discuss the algorithms which are covered in the week 9. So
Sir, which platform you are talking about?
competitive platforms, there are many platforms, huh? Like in TSSN you use lead code and this hacker rank, all these things. So after completion of the PDSA course, definitely you should move to the competitive platforms like hacker rank, lead code, hacker. There are many actually competitive platforms, and you can start just practicing to solving the problems. Actually, it will increase your problem solving skill. So now you know the algorithms, or you know the efficiency things. Now you can just you need some practice to improve your coding skills. Okay, so this course is just a started like thing. Okay, you understand the algorithms or understand the efficiency. After that you have to do some more time for the practice actually. Okay, because in the play at the placement time they will also provide you some programming problems. If you will not do practice, definitely at that time in the time limitation you can't do. So that practice is definitely required from this diploma level to degree level. Okay, that period do not sit idle, just to practice of the programming problem solving skills. So okay, someone is messing up. What will be the target Friday class? Okay, so target is just discuss the week 9 content. Okay, this is like a summary session of week 9, and Friday session will be the problem solving session for week 9 DP content. Okay, so I hope my screen is visible. Okay, So as I hope you have watched the videos of this ninth week. Week 10 we haven't released any content. Okay, so week 10 is just like a refresher week, and some summary weeks are there from week 1 to week 3. So you can just recap your content. These are very small video, 15 minute I think, but this is just a revised thing. So, like that. Okay, so week 9, dynamic programming basically. Okay, so what is the meaning of this? Is just a algorithm design techniques. As we have already seen some design techniques, greedy algorithm, divide and conquer algorithms. Similar to this is also a one algorithm design techniques. How we can solve the problem in different design. Okay, so what is the meaning of this? So basically, dynamic programming refers to that if we so basically if we can divide the problem into smaller sub problems, and we solve the sub problems and reuse the solution of sub problems to solve the main final problem. Okay, so suppose we have the problem like p. Okay, so I'm just assuming that we have the problem p. Let me use my pen. One second. Okay. Yeah, so suppose we have one p problem, and we if we break this problem into a sub problem like p1, p2, p3, and p4. Okay, and we are solving this p1 problem separately, and we are getting the optimal solution for this p1 problem. And similarly, other sub problem we will solve, and later we will if suppose if at any point we require this p1 problem again, okay, to solve, so we will not solve again this problem. Okay, we will reuse the solution from which we have already done before. So that means solution, optimal solution of the sub problem, we will combine that and we will get the final optimal solution for the main problems. Okay, so we will derive. So you can see the first statement, solution to original problem can be derived by combining solution to sub problem. Okay, and here we are looking for the problems which we are getting the optimal solution. Okay, so most of the problems are optimal problems which we generally solve using the dynamic programming strategy. So like one example is given, some one more topic is given instead of this memoization. So what is the meaning of this memoization things? So that means yeah, Himanshu.
Sir, in the example, it is written insertion sort. It should be merge sort, right? Like breaking and solving. So that is merge sort.
No, that is the divide and conquer techniques. Merge sort is divide and conquer techniques. This insertion sort can also be solved using the dynamic programming approach.
Okay.
Okay, so this is not discussed during this lecture, but that problem can also be solved in the same strategy of dynamic programming. Okay, that version we can convert.
Okay.
Okay, so you can understand what is the concept of insertion sort. Basically, we have like random thing. So 3, 4, 1, 2, 6, 5, like this. So we start basically sub problems. Okay, so we start with the smaller problem. So we are just assuming that this single element is sorted. Okay, so now we are assuming this is sorted. When we increase the size of problems, now we move to the second element, and we just check this element with the previous element, this is in correct order or not. Okay, so now if this is in correct order, so we just compare with the previous element, we just shift this element at a correct position. So 3 4, now this is solved. Okay, so here what we are doing, we are starting with smaller problem, and we are reusing that solution to just getting the complete solution. So now this sub problem is now sorted. Okay, so this part is already sorted. Now we increase the size of again one more value element we will include in this, and we will compare that element with the previous element. So that means this is not in the order, so this will become like this, and again we will just compare like this. So this will 1 3 4. So now this part is sorted, so this sub problem is sorted. So in this way, we are starting with a smaller problem and we are getting the solution of final problem. Okay. So because of that, this is also considered as a dynamic programming approach. So where we start with the smaller problem and we get the final solution using that. So same concept like here, this we are discussing. So we are driving the solution of the main problem by combining the solution of sub problems. So that we will understand by the examples clearly. So another thing is memoization. So what is the meaning of memoization? So memoization just a meaning like we store the result of sub problem at some place. At any point, if we require the solution of same problem again, so we will not solve again. We will just check if this problem is already solved previously, and we have already stored the result for that problem. We will directly use that result without solving again. So this is the like properties of the problems which can be solved using the dynamic programming problem. So there are basically two properties required in the problem. So first property is overlapping sub problems. Okay. So what is the meaning of overlapping sub problems? So that means we are computing the same things multiple time during the solution, solving the problem. Okay. So like in the example below, you can see let me use the this page. Okay, so this will be better. Okay. So now here you can see in this example, you know that this is very common uh, like problem which we have solved in Python course using the recursion. Okay, so here we are just finding out the nth number of in the Fibonacci series, and this is very simple solution for this. If n is less than equal to 1, return n. Otherwise, just take what is the solution of previous one problem and what is the solution for like this n minus 2. So generally we add actually if you know that first term is 0, second term is 1. What is the next term? So next term is just a addition of two last problem. Okay, two previous value. So this is now 1. For next value we will get addition of two previous one. So same thing we can start from the n. So n we are looking for. So what is the solution of n minus 1 and n minus 2? That we need to required actually. So what is the solution for this and what is the solution for this? We will just add these and we will get the nth number. Similarly, if we what is the solution for n minus 1? So this will be n minus 2 and n minus 3. Okay, and just previous two terms. So what is the solution for this and what is the solution for this? So in this way, this recursion is happening actually. Okay, so if you just expand this line, expand this recursive call, so you will get this type of tree structure, and where you will see this type of call will be there. So suppose n equal to 5 we have started. So for getting the answer for Fibonacci fifth number, we need the fib 4, what is the value for fib 4 and what is the value for fib 3. Then we will add these and we will get the answer for fib 5. But we don't know what is the solution for this. Again we will expand this. So now this is a new problem. So now to getting the answer for this, we will again check the value for like n minus 1 and n minus 2. So this again fib 3 and this fib 2. Okay, again this will break and it will move to here. So this 3 will become 2 and 1. So now addition of these two. And initially base condition we have mentioned that if n is greater than equal to like 1, so we will return n. Okay, so if this is 0, it will return 0. If this is 1, it will return 1. So this is like a base case. Okay, now fib 1, this will directly return 1, this will directly return 0 without calling again. So this is just like a recursion base case. And now you can see this calling structure is moving this side, and same structure will also move for this side. So like this is the another call, this will also expand like this. Another side we have already done fib 4, now fib 3, this will again extend this in this like, okay, this will expand. So in this call structure, you can see the same type of calculation we are doing multiple times. So if you see this fib 3 we are solving here, this is also solving here. Okay, that means solution we required at this point also, here also. Okay, fib 2 you required here at this point, this point, this point. You can see multiple place we require the solution for the same problem. So according to the calling recursion structure, this part will be solved first. Okay, this is now you will reach at this point. From here you will get a answer. So this is fib 2. So fib 2, you got the answer like value 2. Okay. So now we will store this result at some place, some data structure. Okay. At any point, if we require the same calculation again, so fib 2 we have already calculated. Here we require this calculation again. So we will not expand again. Okay, so we will not expand or we will not call again. We will directly check if this is already solved. Yes, we will directly read the output and we will return back what is the answer to all this. Okay, so 2, because we have already calculated before this. Similarly, what is the solution for fib 1? We are getting directly 1. Same, at any point we have solved this fib 3, we will store the result. Okay, so fib, what is the solution for fib 3 is like 1 plus 1, 2. Sorry, fib 2 was that 1, not 2. Okay, so fib 3 is required again here. So this will not expand this side or this side. Okay, this process will stop at this point and it will return directly answer from this position. Okay, 2, because we have already solved this part. So this is called as a overlapping problem. So any problem where we are just calculating the same thing again and again. That means during the solution, during the solving the problem, we required a same type of computation again and again. Okay, so that is called as a overlapping sub problems. So same sub problems are occurring multiple times during the solution. So this is one property problem should have. Okay, another property is optimal substructure property. So optimal substructure property said that, so the optimal solution of the sub problem. Okay, because we are solving the sub problems and we are getting the optimal solution for sub problems. So if we are using that solution, optimal solution for sub problems, then we will get a optimal solution for the final global, like global optimal solution. Okay, so optimal substructure means, if suppose if we are like p is the main problem and p1, p2 and p3. Okay, so this is the sub problems. So that means optimal solution of like p1, optimal solution of p2, optimal solution of p3. If we combine these, the solution to get the final solution, that should also be an optimal solution for the main problem. So that is the nature required in the problems. Then we can apply this dynamic programming approach. Okay, so most of the time these problems will be based on the optimal, like optimal requirement. So what is the maximum in this, what is the minimum in this type of things. Okay, so now the example is, you can see how we can improve this structure. So first concept is memoization. So memoization is also called as a top down approach. Okay, so top down approach, we use the recursive things, but during the recursion, or we also called as a top down DP. Okay, so memoization, where we use the memoization concept, and we also called as the top down DP problems. So what is this? We are starting from the top main problem and we are just calling the things recursively. Okay, we are calling recursively and just moving to the sub problem. So okay, at the base case, till the base case. But when we are solving the problem from the base case, then we are starting storing the result of sub problems. At any point, if that same problems repeats again and required again, then we will directly get the answer from our memory. Yeah, Disa?
Sir, could you please repeat again?
So
Memor
memoization topic is like we store the result of the sub problem at some place. At any point, the same problem required again to solve, we will reuse the solution directly, because that is already stored in our data structure. So let me just show you this code. You can see here we have taken this memo. Okay, this is just a variable and this is a dictionary. Because why we are using dictionary? Because we can directly fetch the result constant time from the dictionary. Okay, so suppose we have got the result like fib 2. Okay, this solution is we have got 1. So this solution we will store in our memory. So that means for this 2 value we got the answer 1. At any point, if this is required again, we will directly check our memory dictionary if this solution is this value is already exist or not. If this is exist, we will directly read the solution without calling again fib1 or fib0 like this. Okay, so here you can see we have taken this dictionary, we have start this fib n. Okay, this is the recursive call, this is just a base case. Okay, so base case, you can see if n is less than equal to 0 equal to 1, we are storing the result into our memo dictionary. So that means like memo, this is just a dictionary, and from this dictionary we are storing the result. So that means 1 is the key and answer is for this one. Okay, 0 is the key, answer is 0. So that dictionary we are making. Okay, next time we are checking if n not in memo, if this our n value, so suppose we have started n equal to 5, this is now a base case. Okay, and we 5 initially, memo is not empty. Okay, so memo dictionary is just a empty, so we are checking 5 not in memo. Okay, so that we are calling memo n equal to, so memo means 5, we are just getting the solution for this, but this solution we are getting fib 4 and fib 3 like this. Okay, so that means in the previous structure, if I delete this, so recursive structure is same, but what we are doing at the point, so when we are reaching at this base case, okay, so this is just a recursive call, this will happen. So first we will move this side, then this side and this side, and when we will reach the base case, here this memo will store the result. Okay, so this is just a dictionary, so from here 1 equal to 1 will be stored. Okay, and we will move back, and now this is another call fib 0, so 0 colon 0 will be stored in our dictionary. Now we got the result for fib2. So what is the addition sum of these two values? So that is just like a 2, the solution is 1. Now we will move fib3. So for fib3 another call is there, so that is required. So now we will not calculate this again. Okay, so this is just a base case, so again this is already exists, so we will directly read the answer. 1 is there, yeah, 1 we will return back that. Okay, now we will get the answer for 3. So 3 is just it 1 plus 1 2. Okay, in dictionary at the time when we are moving here, so this call will be moved. So fib2, this you can see, now we are required to solve this part. Now already 2 is exists in our dictionary. Okay, that means solution for 2 is 1, so no required for this part. Okay, we will directly return answer 1 here. Okay, so this part directly return 1, and now we got the answer for 4, because 4 is not still exist, so that we first time we got, we will store the result. So 2 plus 1 3. Okay, now we move back here. So fib for 5 we need to calculate this part. So fib 3, now you can see 3 is already solved previously, so 3 solution is already exist in our memory dictionary. So that solution is 2, so 2 will be written directly here, this part will not be calculated again. Okay, and 2 will directly return from our dictionary because this keys exist. So 2 will return for this, and it will store 5, there 3 3 from this side, and plus 2 5, like 5. Okay, and now we got the answer for this. So you can see this part we have saved, this part is not calculated again. So in this way, so this mostly become a order of n times, so most of the calculation actually removed. So if you see this structure like here, so now these are the call will be happen if we store the result in our memory. So this is just like a dictionary. Okay, k value we are storing, and what is the solution for this. So only this call will be happening. So lower part is now not required, lower part not required. So that call will be not be happen. So this is mostly will be like a order of n calls in this way. So otherwise, how many? What was the complexity for this structure? If we are using this structure in the recursion, so that was a how much?
Exponential
2 to the power n.
to the power n.
Yes.
Well,
So
n
now,
minus, okay, yeah, n.
okay, 2 to the power n. Now we are getting mostly order of n. So you can see how much we are improving.
Hmm.
Okay, so this is just like a memoization and top-down techniques, top-down DP. Okay, so top-down DP means we are starting from top problem, and we are just recursively calling to the base case, and then from base case we are solving and we are storing the result, and we are reusing the result. Okay, and then we are getting the final solution. This is the one way. Okay, another is bottom up approach, bottom up DP. So that is start with the sub problems. Okay, here we are not starting from the main problem, we will start from the sub smaller problems, and then we will get the final solution. So what is this type of approach is? So you can see this structure, that will be the easy. So now we can assign like this. So we can assign the solution for 0 is 0, solution for 1 is 1. Okay, in some tables you can just make a list like this. Okay, 0 1, and what solution you require, like 5. Okay, so 1 2 3 and 4 and like 5. Okay, suppose you require the what is the fifth term of the Fibonacci series. Now you know that 0th term is 0 and 1th term is 1. So here you are starting solving the problem into sub problem. So that means you are just considering that if problem is this, if you are asking 0th term, so that is 0. If you include this also, so what is the 1th term? That is 1. Now, if we want to just solve this, so what is that second term? So for second term, just read two values. So this one and add. Okay, so that means just read the previous two solution. So that we are here also we are reusing the previous subproblem solution which we have already calculated. Okay, so that means 0 plus 1 equal to 1. Now for solution for 3, so you can see for 3 we will not calculate again this what is the solution till 1 and 2, like 0 to 1 and 2. We will directly, because we have already solved this part, so we will directly read two value from the previous one and we will directly add and we will get, so 1 plus 1 2. Okay, for fourth, same things. If we want to we want find out like this what is the fourth Fibonacci number, we will not calculate from the starting again, we will just read only previous two because that sub problem is already solved. We will directly read the solution for this, what is the solution for 2 and what is the solution for 3. So that is 1 and 2, 1 plus 2 3. So
Sir,
this way,
uh, is this array you making, is this only for demonstration purpose or we require size 5?
no, you can maintain any data structure where you can reuse the solution. So in this we are using the like array, you can see we have just,
Yeah, like
okay,
I was
so we can
thinking,
here, huh.
uh, can we do it in a size 3 array? Like I am just using, I mean, remembering the last two values and using that to calculate third value and then removing
That,
the
yeah,
first.
that is a like space you are reducing. Yeah, that is also a good way.
Yeah.
Okay, what we are doing, we are just reducing the time complexity, but next thing is how we can improve the space. So that
Hmm.
you are just talking about if you just maintain two variable. Okay, and
Yeah.
maintain the previous two value for on that two variables and calculate the next and again change the value of last two. So
Hmm.
that is just a space improvement. Okay, here we are just using the array. So because in this course we are not much focusing, but that is also a good if you are looking for the space efficiency. Okay,
Okay, sir.
so
Okay.
here we are maintaining like a one array, that is just we are maintaining 0 and plus 1. So 5, if we are looking, that means 6 value we are assigning with 0 0 like all this. Okay, this is just initialization. Okay, after that we are starting t1 equal to 1, so that means we are updating this value 1 1. Okay, so we got the solution for two sub problems, so this is 0, this is 1, and we are running a loop 2 2 and plus 1, so this position. Okay, and what we are doing every time, we are just taking two previous value and adding. So for this position, what is the solution of this? 1. Now for this position, 1 plus 1 2. Okay, for this position, 2 plus 1 3, and for this position, like 3 plus 2 5. Okay, so this is like a fifth term. Because of that we are taking, because our term is starting from 0th term, so because of that we have taken one more size. Just someone is then this, yeah.
Sir, I did not get second line.
This is just like an initialization, that means we are just creating an array and multiplying multiplying this by this size n plus 1. If n equal to 5, 5 plus 1 6. So this creates an array of 6, like 6 size, all initialized with 0. This is like some shortcut actually for the initialization in Python. Okay.
Replication operator for Python is.
Yeah. So we are just assigning all zeros at that number of times initializing. Okay.
Okay.
So our array will become like this by this operation. So in this way, you can see we are just running a one linear loop, okay, from 2 to n plus 1. So now overall complexity you can just observe here, order of n for this operation. So this is called as a bottom-up approach. We started with sub-problem and we use the solution, optimal solution for sub-problem, and we calculate the solution of bigger problem, and finally we calculate the solution of overall global problem. So this approach is called as a bottom-up dynamic programming. And here we also remove the recursion. Top-down approach, we required a recursion, and recursion also has some overhead actually to store the into the stack and memory, all these calls overhead. But this way, we are also not using recursion. Okay, so that is also more improved code. Okay, so now this is the one example to understand how we can move from recurs recursion main recursion to memoization, then memoization to directly bottom up DP. Okay, so yeah, otherwise, so this is not like in the OPP exam, suppose. Okay, we mentioned that one problem will be based on the DP. So DP problem can also be solved using recursion. Okay, so you can if suppose if you can think about if you find out you can solve that problem using recursion. So generally we not test the complexity in the OPP exam for this DP type of problem. So if you find recursion way easy to solve that problem, you can try. Okay, so that is the time limitation exam, you have only 2 hours. So that problem can also be solved using like this. Recursion is just a like checking the all possibility, okay, and then getting the answer. So but here actually we improve, we reduce our repetition work in the DP approach, so that calculates in smartly actually without calculating the same thing again. Okay, so OPP exam you can you think about the recursive approach also for that problem. So recursive approach will try all possibility and will get the answer. Okay, so now this is the one problem which is very easy. Now another problem is discussed like this dynamic programming problem, grid path. Okay, so how this problem can be solved using the DP approach, and here we will show you the all possible things. Like what is the first, what is the problem actually? Okay, so you have one grid. Let me reduce the size. So you have one grid and all these lines are just consider that these are the path actually. Okay, and the condition is in one step you can move to the right or move to the up. Okay, at one step, that is the place you cannot move to the like right left side or down side. So in this way, this is the starting point 0 0 and this is the end point 5 10. And how many paths are possible? Okay, how many paths are possible? So some lines are given, you can see by the color, so blue line, yellow, and that line, this is the possible path. So another are many possible paths are also there on these lines. Okay, but you need to follow only these things, you can only move to the right and you can move to the up side. Okay, at one step. So one step is just like if you at this position you can move this side, so that this one step. So in this way, how much paths are possible? So this is the problem. So there are lots of paths possible, you can see there are multiple way you can turn any side. Okay, so how we can solve this problem like slowly and we can get the solution. So initial first steps you can see okay in this. I'm just explaining here. So initially what we can do, we can just take a smaller problems. Okay, so these are the point like 0 1 2 3 4 5. Okay, and 0 1 2 3 4 5 6 7 8 9. uh 5 is here. Okay, 0. Oh, sorry,
Sir,
I'm
we
just
have to
making.
start from 1 now on y-axis.
Yeah, 0 is already there. 1 2 3 4 5 6 8 9 10. Okay, so now we start that 0 to 1. What are the possibility of path? How many paths are there? Okay, so if you want to move 0 to 1 point on the this x-axis, okay, horizontally. So how many paths are possible for to reach this 0 to 1? Can anyone tell me?
Two, sir.
How you
1,
will,
sir.
how two paths are possible?
So 0 to 1 directly, and
Huh?
then from x-axis 0 to 1, and then 1 to 1 with y-axis.
No, you cannot come on the downside. Like suppose here you can move because this is the constraint. You can either move this side or either move this side. So in this way you can move 0 to 1. This is correct, but you cannot come like this because this is not valid.
Okay.
Okay.
Yes, sir.
So in this way you can only reach to this horizontally one at only one path.
Yes, sir. One part.
Okay. So one path is possible. Similar for 2. 0 to 2, how many paths are possible?
2
I'm just
parts.
looking. No, I'm looking only path, not the steps. Okay, so just count the path.
One, only one.
One.
Only one. Okay, so 0 to 1 and 1 to 2. This is the one path actually. You cannot come from another side. Similar 0 to 3, only one path possible. Okay, 0 to 4, only one path possible. 0 to 5, only one path possible. Because you can only move this direction. Okay, so one path possible. Similarly, here also on the this vertical axis side, same. How many paths are possible from 0 to 1? Only one. Okay, because you can just use this path. Here also 1 3 1 1 1 1 1 1 1 1. Okay, because you cannot use this left to right. Okay, sorry, right to left, this path, so you cannot come from this side. Now this is just like a smaller problems. We have solved this smaller problem and we can make this as a base case. Okay, so this is just like a base case, and now we will use this to solve a bigger problem. So now we are looking for this point. How much paths are possible? So either you can come from this side or you can come from this side. Okay, so that means two paths, and that is the meaning. You can just read this value and this value and add this. Okay, so 1 plus 1, two paths are possible. So that means we have already calculated the solution of sub problems. Now we are directly get reading the solution of that problem and getting the solution of another problem. Okay, now suppose if we are looking the what is the solution for this point 1 and 2, sorry, 2 comma 1.
3.
So same things, till this point we have two path. Now that you can use this path. Okay, so that means till this 1 point you are reaching two path. That means two paths are possible from this side, and one path is possible from this side. So that means just use this two value, use this one value solution. So 2 plus 1, 3 paths are possible at this place. Okay, and the same thing if you want to calculate this 3 plus 1, 4 paths are possible. So now we will just use this inductive structure, same things. So we are just reading the previous value, like previous adjacent value. What is the previous adjacent value which we have already calculated, and what are the lower adjacent value of point. and we just add this. So 4 plus 1 5. Okay, and this way 5 plus 1 6 paths possible. So in this way you can solve this row wise, or you can also try with this column wise. Okay, vertically, horizontally we can solve, vertically we can solve. So anyway you can solve, and just complete the base case and just get the solution like this. Okay, so that means for the next point, this point, how many solution will be there? So 2 plus 2 4, and for this point 2 4 plus 3 7, and here this point 7 plus 4 11. So just we are just reusing the solution. 11 plus 5 16, and
16.
here 16 plus 6 22. Is this correct, or any place we got the mistake? Sorry, 1 plus 2, this is correct. Yeah, 3. I just need this value. So 1 plus 2 3, and 3 3 plus 6, 6 plus 4 10, 10 plus 5 15, and this is 21. Okay, so I just read this value. Okay, so in this way, now how much time actually you are using? So same things, we will calculate this row and like this, and we will get reached at this point to, and we will get the final solution. Okay, so how much time complexity will be required? So how many points we are calculating actually? So total we have 5 and 10. Okay, so actually points, this is just like a base case, and after that we have 5 into 10, 50 points calculation we are doing. So suppose if the like n into m size, this grid is there, so that is complexity is n into m for this. So this you can see we have started with smaller problem, and we reusing the solution of a smaller problem, and we are getting the solution of final problem, global problem. Okay, so this is just like an inductive structure. You can see how we can make this inductive structure. So first we can set the base case. Okay, so recursion solution is also contain the base case. So we can also set some solution for the smaller problem, just like directly. Okay, and that's smaller problem we will reuse to get the bigger problem solution. So after that we are using this inductive structure. You can see we are just taking the solution from this side and taking the solution from this x point, and we are getting the solution at this point. Okay, so this is all defined in this algorithm. So how to solve this, and now you can see this type of points we are getting calculation. But the additional problems may also be asked like this. Suppose this is a path, grid path, but some blockage are there. So suppose this is the blockage point, you cannot cross this point. Okay, suppose this is also a blockage, you cannot cross this point. Okay, so any path you cannot come at this blockage, you cannot use this path, okay, due to this blockage. So because how we can solve this, just assign 0 value for that, because this is the point where there is no path possible to cross this. So 0 is the value for this, and then do the same process. So in this C, you can see this is the blockage is defined. So we will do the same thing. We will start from the base case here, base case this side. After that, we will calculate either row wise or column wise. And we have calculated this, we have calculated this. But at that blockage, we will just assign it 0, because no path can be used this. So to calculation for this point, you can see 6 plus 0, 6 we are getting. So till at this point, only 6 paths are possible. We cannot come through this path. So we will consider this as a 0. So this will change the value of the calculation. So same things here, 26 plus 0, 26 will become. So this is just like a bottom up approach DP problem which we are following. Same can be solved using recursive approach. We can start from this point and we can just call this and call this point. Okay, this point will be called this and like same thing this point. So we can start like solve this 5 comma 10. What is the solution for this? Now this solution is required 2 points. What is the solution for this? Like solve 4 comma, like this is the point. Okay, 10, 4 comma 10, and what is the solution for 5, 9. Okay, so again this problem will be break in the recursively. So in this way we will reach at the base case. So this is the base case actually, which we can directly define at this path. This is the base case, and this path, this is the base case. So this recursive structure will expand till this, either this 0 point or this 0 axis. Okay, so either column will become 0 or row will become 0. At that we will directly return the answer 1, 1, 1 like this. Okay, and in this way this can be solved recursively. Okay, and same thing can be used memoization. Okay, so we will just, because multiple place, you can see this point is required for this point. Okay, so I have a one, and this is also required from this side. So multiple solution we required, that means so we have the overlapping substructure, so that can be solved using the memoization technique. So all solution I have mentioned in this is not discussed in the lecture, but I have mentioned in this notes. Okay, so you can see this recursive, okay, grid recursive approach. So this is for barrier. If we can also define the barrier, if we have the barrier list, so that barrier list we can mention. At that point, we will consider the result as a 0. Okay, so that is the directly we can use.
Sir, what is the meaning of barrier here?
Barrier means we can not cross, use the path from that point. So suppose this is the barrier, so our path cannot become like from this point. Okay, so we can either use this side, we can use this side, like, but we cannot cross this point. Okay, so this path is now blocked, we cannot use this path, we cannot use, so this is just like a barrier, we cannot use that path.
Okay, sir.
Okay, so if some barrier are there, then how many paths are possible? This is also one variant of this problem. So this is one more interesting scenario. So suppose these are the variables, sorry, these are the barrier points. Okay, we have the starting point at this 0, 0, and this is the ending point we require 5, 10, and these are the barrier points. So barrier points contain the 0 possible path from this point. So which strategy is better for to solve this? That bottom up approach or top down approach, which will be the better for this? Any idea, anyone? Bottom up approach, where we will start, this is as a 1, 1, 1, this is the base case, and okay, so we will start to calculate each point like this. Okay, and like this, and then we will get the solution. So this is the bottom up approach. Top down approach, recursive approach, we will just check the solution for this point and this point. For solution for this we require this solution and this solution, and like this. Okay, so every time we require this, so this will start from the top. So which approach is better for this scenario?
Bottom up approach.
Yeah, no, not bottom up. Why? Because what will happen in the bottom up approach, we will do all complete work. That means m into n into m. Okay, so n is just like as a vertical size and m is just a horizontal size. So that means these are the barrier, we don't know what these are barriers. So still we will, our bottom up approach calculate each point, and then we will get the this is the barrier. Okay, so all part will be done. But finally, because barrier directly contain the 0 value, so we don't have the don't require the solution for this barrier, because this there is no path possible from this. But bottom up approach is still solving this complete yellow area, all these points. After that it gets, this is the barrier point. Okay, so there is no use of this calculation actually in this, because we already know the barrier point contains the 0 solution, 0 path. But top down approach is basically, will call this point. Okay, and next point, this path we will directly return the 0 value. So this call will not be happen for the lower side. Okay, so our call will be reached till this point only. So this call will come till this point, and from this we will get the result. And base set, like this area will be calculated, only this part, F1. So only these points will be calculated. This yellow region will not be calculated by the top down approach, because we will directly get the answer from barrier point. So in this scenario, our solution will be calculated using m plus n operations. But bottom up approach is taking n into m, all calculations, all point calculations. So this scenario, top down approach will work better, but this is just like a some rare scenario, okay? But most of the time our bottom up approach is efficient, because this is just like a rare situation where this type of blockage is there. Okay, so this is just a lesson in this. So complexity is using dynamic programming, but using memoization we are getting this m plus 1 n. So this is better for this some rare scenario. Otherwise, most of the time this DP bottom up approach is more efficient, because this not contains the overhead of recursion also. Now all types of that implementation are given for this. You can see this is just a grid recurrence. Okay, we are not storing the result, so this is just a recursive call. All points we are checking from bottom up approach, sorry, top down approach. Okay, you can see similar of the previous calculation of the like Fibonacci series. We are calling at this point, and we are calling at again this point. This is become as a base case. Okay, we are not using any memory for this, so this is simple recursive solution. Now memoization, the solution is very similar, same recursive calls are there, but we are storing the result of base case. Okay, this memo table. At any point, if you can see same things, we are checking this point is already exist in the memo table, we will directly read the answer from solution from memory table. Otherwise we will calculate by the recursive call. So here we use the memoization. That means this is a top down DP memoization concept. So this will save our repetition work, but this is also a recursive solution. And the final solution is this DP bottom up approach. Here we are this, you can see there is no recursive call. We are considering we are making this as a base case, and first base case for the all x line, x axis or y axis base case. After that we are just calculating all points. So this nested loop you can see are just calculating all points of the solution, and by using this inductive structure, this one. Okay, just the left point and bottom point, add this and getting the solution for this. Okay, if at any point barrier is if any point in barrier, so we will directly assign the value 0. So this is just like a one nested loop is there. Okay, otherwise so this is also a initialization for the all points, not all points. Yeah, if I equal to 0 or j equal to 0, then we will assign only one value, that is the just borderline. Okay, so this loop is also n into m, and this loop is also n into m. All are separate, so overall complexity will become n m. Here xy is there, so xy we can consider. So this is just like a basic iterative solution. Okay, this is bottom up approach. Okay, so in this way we can smartly solve the problem in the efficient way using DP approach. So these two problems are discussed. After that, some very standard problems which is solved by the same DP approach are discussed in this lecture. One is longest common subword. Okay, we have two strings, and in these two strings we are finding out a longest subword. Word means continuous actually strings. Okay, suppose you can see this example. So one string is this secret, this completed, okay, and another is this bisect. So what is the continuous sequence of substring which is matched actually in both? and what is the maximum length for that. Okay, so you can see SEC, this is the continuous strings. Okay, and same SEC here also, this is continuous, so which is matched, and this is the longest actually, maximum length substring which is matched. So this problems, this is also very use is also very common, like you know about the plagiarism actually. Okay, this is the one thing, subword, and another next is longest common subsequence. So subsequence we can skip some character, okay, but we cannot change the order, but we can skip some character. Like in these two strings, SEC is also matched, but after that in the same order T is also matched. Okay, so SEC and T, we can skip some character, but order will remain maintained, so that SEC is come first, so SEC is come first, then T is coming, then T is coming in this also. So then what is the longest common subsequence? So this is called as a common subsequence, where we can skip the character, but we maintain the order in common strings. So these requirements actually used to just like a one very common application as a checking the similarity in the documents. Suppose we have two documents and we are checking how much that documents are similar. So like very common example which we use in our program. So you know that in the med course, med 1, med 2, you submit the project. Okay, after that we check the similarity of the each student's project with the other student project, how much projects are similar. So that actually gives the information that how much students have copied to the from the others. That is called as a plagiarism. Okay, so this is very common thing. So some research paper, many researchers are published the research paper, so that is also check that how much part they have written by your own, or how much part they have taken from the others resource. So that plagiarism information is checked by this similarity. Okay, common subsequence, or next problem is edit distance, that is also provide the information of the similarity. Okay, so same concept we use in our project plagiarism. Okay, how much students, sometimes we got like 100% similarity in two project submissions, so that we actually reject. So how we can solve this? Okay, this is also very difficult task. If you think about the naive approach of for this is very difficult. So because we have two substrings. Okay, suppose you have one A, B, C, E, F, and another string is like B, C, D, A, B, C, D. Okay, so because any part of the first string can be matched from any part of the second string. Okay, that is not just like a AB will always match from the starting. So this A, B, C, D, E, F can be matched from this position. But for checking purpose, we have to check everything. We have to check this A part from the starting, how much this is matched with the second part, like this. So that is not very easy task by the naive approach. Okay, so how we can find out these things? So what is the longest common subword is matched in these two strings? So same things, we can use the DP approach for this, and we can start with the smaller problem, and we can reuse the solution of smaller sub problem, and then we get the final solution. So this is one problem. Okay, so LCW, longest common subword, because here this time we are working with two substrings. Okay, sorry, two strings S1 and S2, and we are looking for the common substrings with the maximum length. Okay, so now that means to check this we required a checking for each part. Okay, so that means uh, this part should be checked with each part, like first position, second, third, first, okay, every part of the other strings. Okay, same, this part should be checked with. So all possibility we need to check, but we want to reduce the repetition actually. Okay, so that means if we have checked one things one time, so no need to check again that part. So how we can do this? So we are just making a two-dimensional data structure for this. Okay, and then first thing we are making a base case. Okay, so how we can solve? Suppose this 6 point. Okay, we are taking one additional size. So this, just assume that this is a S1 and this is a S2. Two, okay, dimensional we are storing. So this two array we have. So that contain this strings and S2 contain this string. And we are storing the result into a two-dimensional because we are calculating the each compare possibility. Now we are also taking one additional as a base case. So this point, this is not a part of our strings. Okay, this is not our part of string, but we are making this as a base case. Suppose S1 string is empty string, S2 string is empty string. Then what would be the matching actually? Okay, just consider this line only, solution for this and for solution for this point. Okay, so both strings are empty, so this is the point for this. If S1 and S2 both are empty string, how much characters are matched? What is the level of maximum matching? 0. Okay, there is no character, so that means we are directly put the solution for 0. Still, if you have S1 equal to empty and S2 you have some character, okay, maybe one character, two character, three character, any character like A, B, C, D, still you will get a zero matching because this is empty and this have some content. So how many characters are matched with the maximum length? So zero matching. Okay, because of that we are just using this string S1 as a empty, but corresponding if we have one character, still we will get zero answer. If we have this et, then still we have zero answer. Okay, so any string is there and we are assuming that S1 is empty, this point. Okay, this only. So this complete row will become 0. Similarly, reverse thing, if S1 have some string, any character 1, 2, 3, any character, but S2 is empty. Okay, so now this will become 0. No actually substring you will found if one string is empty. Okay, so corresponding we are looking for, if we have we are just assuming that starting from the smaller problem and we are getting the increasing the problem actually. Okay, initially we start with empty string 0 point, then we are assuming that our this S1 have t. So what is the solution for empty string with S2? 0. So now these two rows become a base case, like, okay, some solution of smaller problem. Now we will use this, okay, to calculate the solution. Now we will solve this either row wise, either column wise, or you can also solve horizontal, that like vertical, this diagonally, like any way you can solve. Because now you can just understand this inductive structure. This is important, you can remember or you can learn this for these very common algorithms, very standard algorithms. So after making this structure, this base case, then this is the things. If ai does not equal to bj, so ai is a one string and bj another string, and I and j are just a index for that. If that characters are not matched, we will directly put 0. Okay, if characters are matched, so we will use what is the value, what is the solution for this point, this point. Okay, I plus 1 and j plus 1, that means like a previous right point and previous bottom point, like, okay, in this, and we will add 1 because this is the condition. We will get a continuous matching actually. So like suppose if we are looking, so this base case, I hope this is clear how we filled this. And now how we will reuse this. Okay, now we are increasing the problem size. So suppose we are calculating what should be the matching at this point. So at this point we have the S1 only t. Okay, t. S2, what is the only t, that is also t. So we are just looking at this smaller problem. Okay, so before this, if characters are matched, if characters are not matched, directly put 0. Okay, but if characters are matched, then we will look what is the previous diagonal solution for that. Okay, so like we will just read this value, because this is making a continuous matching. This diagonally information will ensure that you are just consider continuously finding the matching, because we are looking the subword continuous maximum length which is common. So which we will look this position, what is the value of this, and we will add 1. Okay, so 0 plus 1 1. Now that means in this string and this string, what is the maximum common thing? Only one character. So we got this one information. Okay, so same way we can just fill these things. Okay, so in this place, now this side we have only s1t, but this side we have now increased our, okay, et s2 equal to et. Now what is the solution? So sorry, for this position, this character actually will look. So this character actually e. Okay, this side e t, this side e. The characters are not matched, put 0 directly. Okay, for this point, character is t and this side r not matched, 0. So same, all characters are not matched, 0 0 0 fill. Okay, so this row is completed. Now we can fill this row. Okay, now because every time we require this diagonal information, so we should have the complete sub problem solution available. So now at this position, c is there and t this there, directly put 0. Okay, c is there and like this is e. Okay, so this is also not matched. C and r, this is also not matched, but c and c, you can see this is matched. So c and c, this is matched. So what is the diagonal? So that means what are the previous solution we have continuously matched? So 0 solution. Okay, so that place 0 plus 1 1. Okay, because this value t and r was not matched, so this is not a continuous matching. So one value we have got, then 0 0, because the characters are not matched. Next time again we will fill this. So same things, e and t not matched, e and e matched, so we will just put the diagonal value 0 plus 1 1. Okay, but at this point you can see now e and e, this is matched. So we are looking the previous solution. So what's the previous character status? Okay, just previous characters c and c, yeah, that was also matched, and that is the continuous matching. So we will add 1 plus 1 2. Same things you will get here. So like s, you will get a previous solution. What is the maximum length which you got at that point? So that is 2 plus 1 3. So in this way, we will compute all value, and finally we will get a maximum among complete matrix. What is the maximum value at the complete matrix? So here we got 3, here we got 1. So maybe some place, you suppose you got like this structure, and you got like 1 2 3 4. That means these all characters are matched. So in this way, we will return a maximum among all values. So that is 3. So this is the information that the common subword maximum length is 3, which are common in two strings. So that is the solution of n into m solution, because we are computing these number of questions. Okay, so in this way you can identify that what is the common subword with the maximum length. Okay, so that is the algorithm. You can see this inductive structure is important, and after that you can simply fill this matrix by just reading the diagonal value. Okay, that become a longest common subword. So the code is also written in the same way. First we filled all the complete matrix by 0, okay, by the direct calculation, and then we are just looking for the maximum value in the among all calculation. And each point we are calculating, if we are getting both characters same, we are just reading the diagonal value and plus 1, otherwise directly put 0. And every calculation we are calculating, if we are getting the current value greater than the previous maximum, we are just storing that. Otherwise, later you can directly return the maximum, okay, of the all field, return max. So this is longest common subword. Complexity is m into n. Now the similar problem, longest common subsequence. So as I mentioned that subsequence, we can drop some letter in between, but we cannot change the order. Okay, so that is called as a subsequence. So in this strings SECT, this is 4 length is matched as a common subsequence. Okay, so what inductive structure some we will actually change here. So same things if characters are not matched, because here we need to maintain the previous match. So because we can skip the character, okay, previous in example we cannot skip, but here we can skip. So suppose if T is matched, so this first T is matched with this T, but after that this E is not matched, R is not matched, but that C is matched at this place. So previous value we also retain actually. So what is the previous character maximum length we have maintained? Okay, so one length we have maintained. For C this point, we should get the 2 value. That means till that point, 2 subsequence length is there. So previous solution, if our characters are not matched, so then we will not put 0 here this time. We will just put the what is the previous maximum solution we have at this point. Okay, so that is the only change in this algorithm. So this time if characters are not matched, we will look all positions. So look all position either right side or left side. Okay, what is the maximum solution of the right field and bottom field, and then we will return that as a solution. If our characters are matched, we will read the diagonal value and +1. So this is the thing. So here same thing, base case is the same as I mentioned in the previous. Empty string, no matching, 0 matching. After that we will just match T is matched with T, so we put 1. Now T is not matched with E. Okay, so in this place, because we have already matched one thing, okay, T and T matched, one length is matched, so we will not remove that information. So we will maintain that. To putting here, we will check what is the this bottom value, what is the right value, which one is the maximum. So that value we will put here. Okay, same thing, T is not matched R, so what is the right value, what is the bottom up value. Okay, so what is the maximum among them, that we will put. So that is just retaining the information that how much length we have already matched till that point. So that we have matched one length TT. Okay, at any point if our characteristic is matched again, so this line you can see we are retaining this information. So if we have S1 equal to T, okay, and S2 we have all this secret SECRET. So what is the maximum common substring length? Only 1. Okay, so this is defining this information. Now next information you can see C is not matched with T, so we will just put max of this bottom and right 1. Okay, so all this information we are getting, but C is matched with C. So at that time we will just read the that diagonal value and +1. So 1 + 1 2. So previous it was if characters were not matching, then we were putting 0, because at that time we required a continuous location, but this time we can skip. So same E, we will just 2 + 1 3. For S continuous matching, then 3 + 4 this 4. And after that it is not matching, so we are just looking what is the maximum value of both sides. What is the maximum value of both sides? So in this way we will always get a maximum value at this point. Okay, because always we just look right or bottom and we will update that. So during the calculation you will always get a final maximum value at this point, and that will be the answer as a maximum common subsequence length. Okay, so code change is only this. The same thing we are doing, we are filling all 0 at this place. After that we are just iterating all this loop. If our characters are matched, we are diagonally reading and +1. If our characters are not matched, we are finding out the maximum of bottom and right value. This. and finally we are returning 0 0 position value. So that will return a maximum length of common subsequence. Complexity is same, I mean to n. So in this way you can see all these are actually bottom up approach. So we are starting with this very smaller problem, empty strings, and then we are calculating this all possibility. And so this is now one more algorithm, edit distance. This edit distance is also very similar, but this return a minimum difference in two strings. This is just like a reverse of this longest common substrings. Okay, what is the minimum difference in two strings? And basically we have three operations. So like we have s1 equal to a b c, and s2 equal to like a b uh, d. Okay, so what is the minimum difference in these two strings? So operation, so what, how we are just calculating the difference? So that three operation we are supporting, we can insert a new character, that is just as a one operation, delete a character. Okay, that is just like one operation, and update the character, that is just as a one operation. So here what is required, if we update the one character. Okay, so a b and these are common, and so how many minimum operation are required? So that is the task. So this is the same part, but this is different. So suppose if we actually update this by c, so now both become same. So what minimum operation we required to make both strings same? So that is the edit distance. So that means one operation we required update here. Okay, so for to make the same. Suppose we have s1 equal to a b c d e. Okay, and s2 equal to like only a b. So then how many operation we minimum required to make both the same? So either we can insert three character, okay, c d e, then both become equal. Three operation is required, or we can either remove three character from the above one. So remove, that is also three operation, so both become same. Three edit operation is required to make both the strings same. So this is just like a edit distance. This is also required a also provide the information of similarity. If edit distance is very low, that means our string is very similar, high similar. If edit distance is high, that means our string is not similar. Yeah, Disa.
Sir, could you please explain that again?
Huh.
This,
So edit distance is just representing that how much minimum difference is sorry, how much minimum edit operation is required to make both strings same. Okay, so suppose s1 equal to a b a c like this. Okay, and s2 equal to a b d e. Okay, suppose these two strings are there. Our task is to make both strings same. We can perform only these three operations. We can insert a new character, we can delete a character, we can update a character. So that is called as a one operation. Okay, either insert, if you are performing this operation, one operation is there. Okay, so but our task is this, we want to make both strings same but with the minimum number of operations. So that is the task. So to make both, either you can convert this s1 to s2 with the minimum number of edit operation, or you can make this s2 to s1 with the minimum edit operation. So that is the requirement. So in this is meshed, ab, this part is meshed. So what you can do, you can update like this a character and c character. So you can update a to d, okay, and c to e. So two update operation is required. So that means the edit distance for this s1 and s2 is 2. Two minimum operation is required to make both similar. Okay,
yes,
so so this is our task here, and this edit distance is actually also give the information like how much strings are similar. If this edit distance is very less, so that means both strings are very similar, close to similar. If this edit distance is high, that means both strings are much different. Okay, suppose if S1 equal to like A, B, C, D, or S2 equal to like E, F, G, H, I, like this. Okay. So you can see edit operation will increase in this because both are different totally. So for edit operation you required, update operation you required A, B, C, D, and one delete operation you required. Okay, so five operation is required. So edit distance is become now five to make both same. So high edit distance means both strings are very much different. If low edit distance means both are very much similar. So this is also a one algorithm which is used to find out the similarity in the document, in the plagiarism actually. Okay, so we check the two documents and we check calculate this edit distance. If we are getting this edit distance very low, that means both documents are much similar. Okay, so this is just like as a reverse information of LCS. Okay, so this edit distance is very common in algorithm for plagiarism checking, similarity checking in two documents. So here inductive structure we have little bit different. Okay, because our target is to find out the minimum number of operation to make similar. So they said it, you can see if our characters are not matched, that means edit operation is required. Okay, so in that case we will find out what is the minimum operation is required of the previous sub problems. So that means we have three places. So either left, the diagonally lower, left side, or bottom side. What is the minimum number of operation required in these three problems, that we will select, and then we will add one, because our next character is not matched. To make similar, one update operation or any operation is required. So what is the previous minimum distance we have for sub problem, and we will add one more, because our overall target is to finding the minimum number of edit operations. So we are, because of that we are selecting the minimum of all sub problem solution. And if our characters are matched, that means no edit operation is required. So we will directly put our solution same from the diagonal position without addition. So this is just like inductive structure for this, which we will use to fill this matrix. So here you can see bisect and sacred. So here base case will become different. If one string is empty, okay, and this is also empty, so then edit distance is zero. Okay, both are empty, no actually difference is there. But if one string is empty and another have some character, so suppose some this have only t character, so to make similar you required a one insert operation into one string. Okay, then it will become, so one operation is required. If one string have two character and another is zero, then definitely two edit operation is required to make similar. Okay, so this will become two. So if one string is empty and another have this length of character, so in this way this will increase actually this side. Same for this side, if second string is empty and first string have characters, so how many characters are there, that will represent the number of edit operation. So in this way, now this will become a base case. After that we will fill all the value row wise, column wise, or diagonally anyway. So if our characters are not matched, if our characters are matched actually, okay, tt, then we will diagonally read same value without increment. Okay, if our characters are not matched, like t and e is not matched, then we will look all three side. Okay, so what is the right value, what is the bottom value, what is the diagonal value, and among all these, what is the minimum, and we will add one in this. Okay, so then will become 0 plus 1 1. Yeah, someone raised the hand.
So
Yeah,
please can you explain the base case again?
base case is like, suppose if you have s1 is empty string. Okay, now s2 you have, suppose like a character, then how many minimum edit operation is required to make both similar? So if you want to make this s2 empty, you have to delete this character, so that is one operation. Or if you make s1 similar to s2 if you will, then you will insert a character. So that is one operation. So that means one operation is required. So same situation is there. We are assuming that this S1 is just a empty point, and this side we have one character. To make similar, one operation is required. Now suppose S1 is empty and S2 have two character A, B. Then how many minimum operation is required to make both similar? Either you remove both character, then it will become empty and both will become empty, so same. Or either you will insert two character A and B here. So two operation is required. So because of that, two we are putting
So
here.
do
Okay.
this 1, 2, 3, 4 is the number of operations required.
Number of minimum edit operation is required to make both similar.
Okay, sir.
Okay. So here we are at this to fill this line. Okay. So to fill this line, we are assuming that this S1 is empty, and this side we are just increasing the size of problem. Okay. So for this problem, one character. For this problem, now two character. For this, three character. Okay. So like in this way increasing. Now for this row, this vertical okay line, we are assuming that S2 is now empty, and we are just increasing the character from this side. So this is one, this one. Okay, this is now two length, two is there, three is there, three is filled. Okay, in this way, this fill. And now we are filling the this become a base case. And now we will fill this matrix in the based on that inductive structure. And if our characters are matched, we will read directly diagonal value. That means no change is required. If our character is not matched, then we will look the minimum solution from all possible previous sub solution, because our target is to find out the total minimum operations required. So because of that, we are looking each side. So what is the minimum solution on the right, left, right, bottom, and diagonally? In among all three, what is the minimum value? We will add one. So that we will use. So in this way, we will fill this matrix, and finally we will get the answer at this point. This point. Okay. So this is representing the information of minimum edit operation. So similar type of implementation is again here. We are just putting this first zero matrix. After that, this is just like a last row and last column. Okay. So this I and N, last row, and M and J. So we will directly put the same thing. So this 1, 2, 3, 4, these two steps are just filling this base case. After that, we are traversing all field, and we are just using that inductive structure. If characters are same, just read the diagonal value. If characters are not same, find out the minimum among all adjacent, right, bottom, or diagonal, and plus one. So that means characters are not same, so we need required a one edit operation. But we will just select the what is the minimum edit operation required from the previous sub problems. Then we will add in that one. And finally, at the top, at this position, we will get an answer. Okay. So these three algorithms are very much similar based on the strings actually finding the maximum or longest. So as I mentioned that these most of the DP problems are based on the optimality problem, where we looks for the longest common, like maximum common, or like minimum edit distance, minimum, this type of information. Okay. So this is three problems based on the strings, common things. Now one algorithm is matrix multiplication. So I think this is the last one. This, okay. Matrix multiplication. So you know that how we multiply the matrix. So how many operations are required, and how we can improve the total number of operation in the multiplication. So you know that like we have two matrix. Suppose this is the matrix of 2 by 3. So 2 by 3. Suppose 1, 2, 3 row and columns. Okay, yeah, 4, 5, 6. Okay, and another matrix we have like 3 by 4. Okay, so that like 1, 2, 3, 4, 5. Sorry, 1, 2, 3, 4. 5, 6, 7, 8, 9, 10, 11, 12. Yeah, I've just taken this example. So how we multiply this matrix? To multiply two matrix, this row into column, so R into C, this column should be matched with the another matrix row. Okay, then we can multiply. We can just take this column and we can just put here and we will add this. Correct? If you remember that, how we multiply this type of matrix. Correct, or anything wrong in this multiplication? So we will calculate like this: 1 into 1 plus 2 into 5 plus 3 into 9. Okay, and then same for again 4 into 1 plus 5 into 5 plus 6 into 9. So this will become a first. Then we repeat the same thing again for this. Okay, and same thing again for this, same again for this. Okay, so in this way you will get a computation like this way, and you will get a matrix of 2 by 4. So how many computations are required? So that is the number of, you can directly calculate, like, so if you have matrix by 2 by 3, one matrix, and another matrix is 3 by 4. So how total number of computation is required, like 2 into 3 into 4. Okay, 2 into 3 into 4. So like this, so 2, 3 is 6 and 24. Okay, so that is 1, 2, 3, 4, 5, 6. Okay, and 6, that is like 10. 6 and 6 and 6 total computations, multiplications basically. I hope you got this, how we are counting this multiplication computation. Okay, so total 3 computation for multiplication operations are required for this, 3 for this, total 6, and 6 for the 24, same we are getting here. Okay, so we can directly calculate like this. Okay, so this is the problem basically. Now suppose if you have more than one matrix, more than two matrix, if you have two matrix, then there is no problem, you will multiply them. So suppose if you have m1 m2, two matrix you have, and that follow the that compatibility. Okay, so like you have 2 into 3 and 3 into 4, so we can only multiply this. So this is the only way we will directly multiply. But suppose if we have three matrix M1, M2, M3, okay. Now the compatibility is there. Okay, so like 2 into 3 is there, and 3 into 2 is there, and then 2 into 4 is there. So like then we can multiply this order. Now, but there is two things here. We can change the order of multiplication. Either we can multiply like this: M2, M1, M2 first, then with M3 second. Okay, this is the one possibility of the multiplication. Second possibility is M1, M2, M3. Then just pick this M2, M3 first, and then multiply with M1. Okay, so two possibilities there. If you have three matrix, how many total number of operations will be there if we change the order? Okay, size is given. Suppose if we multiply this M1, M2 first, so how many operations are there? So 2 into 3 into 2. Okay, 2 into, so if I'm writing here 2 into 3 and 3 into 2. So 2 into 3 into 2. This is the total multiplication. And after multiplication, we will get a one matrix, like I'm giving the name of 1, 2, and size will be 2 into 2 for that. Okay. Now then we will multiplying this resultant matrix with M3. So that size is 2 into 4. So total multiplication for this is 2 into 2 into 4. So how many total operations are there? So this is 6, 12 plus 4, 4 just 16. How many? 28. We are getting total multiplication. Now, if we follow this order, then what is the total output? So we are just multiplying 3 into 2 and 2 into 4 first. Okay, so that means this is the first 3 into 2 into 4, and resultant we will get 3 into 4, and that will be multiplied with this, so that is 2 into 3. Okay, so now the addition 2 into 3 into 4, 2 into 3 into 4. So 3 to the 6 for the 24 plus 6 for the 24. Now 48. So you can see here, if we change the order of multiplication, then our total number of multiplication count is also changed. Okay, so now this is the problem, and we need to find out the minimum number of multiplications required during the that matrix multiplication. Our target is minimum number of multiplication. So what are the minimum number of multiplication possible if we multiply multiple matrix? So this is for example for three same, suppose if M1, M2, M3, M4, if this matrix is there, then how many possibility are there? You can see. So we can, one possible is you can either do M1, M2 first, and like M3, M4 first, okay, and then both. Second is you can do M1, M2, and then multiply with M3, and then multiply with M4. Okay. Third possibility is M1, like M3, M4 first. Okay. Then M2, and then M1. Fourth, you can do M1, M2, M3, like middle first. Okay. Then with this, and then with M4. And another is like M2, M3 first, and then M4, and then M1. So you can see for 4 matrix, these 5 possible way are there. So out of these 5 possible way, which contains the minimum number of operations? So that is our task here. We are figuring out that what is the minimum number of multiplication required to multiply these number of matrix. Okay, so that is the problem. So I hope the problem is clear for matrix multiplication.
Yes, sir.
Okay, so now the algorithm. Huh. So here this implementation is given. I'm just explaining the another implementation. So this inductive structure. So here actually what we will do, we will maintain a total number of matrix. So suppose how many matrix we have. So that like suppose we have 5 matrix. Okay, 5 matrix. We are assuming that. So 5 by 5 table we will maintain. Okay, so this is just representing 0th matrix M0. Okay, M0, M1, M2, M3, M4. Okay, same. This is M0, M1, M2, M3, M4. This is like just like we have 5 matrix, and we are just giving the label for matrix is 0 to 4, and that matrix we will maintain. And you can see we are just taking this example. This is little bit tricky or more calculative. Okay, algorithm. So we are assuming that we have these 5 matrix in this example, and the size of these matrix is this one. Okay, so each M0 is size 4 into 10. 10. The next is 10 into 3. So this compatibility should be there. Okay, so we can only follow order. We cannot multiply this directly with this. This order we should follow. So for 4 by 10, 10 by 3, 3 by 12, 12 by 20, 20 by 7. The main thing is we are just looking the minimum total number of multiplication operation. So that we have to check all possibility. But here the DP thing is we will just reuse the solution of sub problems. So we are maintaining this matrix. Okay, because the calculation we cannot change the order. Okay, so because of that only this part is required. So this diagonal part is required to calculate. because this matrix can be multiplied with this matrix. So that solution will, if we are multiplying the same matrix, if we have single matrix, suppose if we have single matrix M0, so no multiplication is required, correct? So this diagonal value is just representing if we have only single matrix. So that is M0 matrix, we have zero multiplication required. If we have only M1 matrix as a input, so only zero multiplication is required. If we have M2 matrix, only zero, M3 is zero, M4 is zero. So this is just like a base case. Okay, we are assuming that we have only single matrix. So if we have single matrix, how we will multiply with this other? We have no matrix to multiply. So that is zero number of operation. Now the next part is we are just calculating this. We are incrementing the set. Suppose if we have M0, M1, two matrix. So what are the operations we required to, minimum number of operations are required. So now this point is actually indicating this. So this is just like a 0, 1, 2, 3, 4, and this is also indexing 0, 1, 2, 3, 4. So this field is basically 0, 1, 0, 1. So this is indicating that we have matrix 0 to 1. Yani two matrix we have, M0 and M1. So what is the minimum operation is required when we multiply these two matrices, M0 and M1? So as I mentioned, if we have two matrices, we have no option. Only one way is the multiply way. So that we will directly multiply, because size we can also maintain here. So M0 is just like a 4 into 10. M1 is a 10 into 3. This 2 is just like a 3 into 12. And next is 12 into 20. And next is 20 into 7. Okay. So if we have two matrices, M0 and M1, so there is only one way to multiply. So directly multiply. So what? How many operations are there? 4 into 10 into 3. So 4 into 10 into 3. Total number 120.
120.
So that value we will directly put here. Okay. Now for this position, what is indicating? 1, comma 2. So that means we have only 1 and 2 to these matrices. So M1 and M2. These two matrices we have as an input for this. We are looking the solution for this part. Okay. So that is just like this one. So 10 into 3 into 12. So 10 into 3 into 12. So this is the solution for this. So this is 360. Okay. Same things if we have two matrices M2 and M3. So just multiply 3 into 12 into 10. So you will get a 720. And if you have matrix M3 and M4, so you will multiply 12 into 10. This 20. This is 20. 12 into 20 into 7. So you will get it this one. So you can see you are getting a solution of sub problem. So that means in this line, single matrix. In this line, 2 combination is there. M0, M1, M1, M2, M2, M3, M3, M4. Now, next time when we will calculate this one, okay, so now this position is indicating M0, M1, M2. What is the solution for this? What is the minimum solution for this? So you can see what are the possible way to multiply. We have M0, M1 first and then M2, or M0, M1, M2 first, then 0. This way. Okay. So here this is the way, because M0 and M1, this is already solved. M0 and M1, this is already solved here. So we will directly put answer for this is 120. And the resultant matrix for this is 4 into 3. Okay. So this part we will no need to calculate, because that we have already done. We will directly read the solution. Same things for this part, M1, M2, that we have already solved, this 360. Okay, so 360 is the solution for this, and resultant matrix for this is 10 into 12. 10 into 12. Now we have this two value, and we will check. So multiply with this M2. So M2 size is 3 into 2. So 3 into, so this solution is already there. So 3 into 12. So 4 into 3 into 12. So add 120 plus 4 into 3 into 12. What is the value of this? Same for second one, 360 plus and 0 is 4 into 10. So 4 into 10 into this 12. Okay, 10 into 12. So this value. Among all these two calculation, what is the minimum value? So that minimum value we will put here. Okay, so 120, you can see 120 we are getting from here, and plus 4 into 3, 12, 12, 12 is 144, and you will get 164. So by this calculation we are getting 164, and this calculation definitely you will get a more than 360. So this one is the smaller one, that is sorry, 144 and 120, 264. 264 we are putting here. So in this way, we are solving smaller problem first, and later we are reusing the solution directly from that. So same way we will put this way. Okay, so this matrix filled diagonally actually. Okay, first we will fill this way, and then we will fill this. Next part this will fill, and finally we will get the solution from M0 to M4 at this point. So always we are looking the minimum one. We select the minimum. So the inductive structure is for this is like this. If I equal to j, so that is the position for diagonal. Okay, so if that means we have only single matrix, we are putting directly 0. Otherwise, if I is less than 0, so this is indicating we will only fill the upper triangle, that diagonal part of the matrix. So in this case, for every ij, so we are calculating the value of Cij. So we will calculate this value. So minimum of the Cik, and so this is already calculated. Okay, Cik and Ck plus j. This is already calculated, and after that we will add this dimension into this, and this things we will calculate for all value of k from I to less than j. Okay, because we have multiple possibilities. So for you can see in the three matrix M0, M1, M2. So there are two ways, so that we can either multiply like this, or we can M0, M1, M2. We can either like this. Okay, two possibilities here there. So this is actually define this structure for k value which is equal to greater than or equal to I to less than j. Just put this in k value here, you will get a all possible way here, but we will reuse the solution directly. You can see Cik, Ckj. This solution we are directly reading from the matrix, and we are adding the additional solution for the multiplication. So in this way, and among all these solution, all for k, we will calculate this, and we will get the minimum one. So in this way, we will fill all matrix, and at the top corner, we will get a minimum this one. This is representing the total minimum number of operation to multiply M0 to M4 matrix. So what order actually we will follow to get this minimum number of operations, that we can also conclude, and that is depends on this k value. So which k value we are getting the minimum value actually. If we will store this information also, so then we can also finalize the total that order of multiplication. Okay, so here M0, M1, M2, M3, M4. Okay, so this is the same thing. Yeah, 0, 1, 2, 3, 4. I'm indexing. So this value actually we are getting from like, because this is only two matrix, so k will remain 0. So that this is actually I, and this is j. Okay, so we are starting from I0 but less than j. So this is the only possibility. So this k value we have stored here. So for this k value we got the minimum. Same for this position. So this is the k value. Is only one possible value is there. So 1, then 2, and then 3. For this part, actually we have M0, M1, and M2. So k is starting from like this is I, so from equal to 0 and less than 2. So that means k is possible 0 and 1 only. So for these two value we will calculate what value we are getting. So which one is the minimum? So we are getting the minimum for 1a. Okay, so that we are storing here 1. So this information we will store which k value we are getting this minimum operation. So with each calculation. And finally, based on this information, we can identify that what order we should follow. So you can see we have initially this order M0, M1, M2, M3, M4. So we will start from this part. Okay. So we are getting k value 1 because this is the final solution from M0 to M4. So this is the k value. So k value is this first bracket we will put here. Okay. So at 1 this place. Sorry. No, so this is not correct. This M1 place. So this is one value. So that means first bracket will be put here and this will become different. So now we have two place 0 to 1. This is the 1. So this is two matrix. This is, we cannot further divide, but here we need to identify that which order should be maintained. So 2 to 4. 2 to 4, just look which value is coming. 2 and 4. This is coming. Okay. So 2 to 4, and what is the k value is here? 3. So just break from the 3 like this. So if you follow this bracket order to multiply, you will get this multiplication count, and that is the minimum one. Okay. So in this way, you can also identify that which order you should follow to multiply, and then you will get a minimum number of multiplication of this one. Okay. So this is the way how we are using the DP approach to identify the solution. Okay, so all these problems are discussed. These 5-6 problems are discussed in the lecture. So that are standard problem, and some additional problem we will cover in the live coding, some examples, and also discuss in the mock. And you can also start with some searching from your side, and I think that our TA will also discuss some new problem on the DP. And in OPP exam, the problems of on the DP will be easy, actually easy only. These are the two-dimensional DP generally we call, where we are maintaining the storage in two-dimensional matrix. But the initial, like this Fibonacci, where we are maintaining the result into one-dimensional array. So the OPP problems will also be based on very simple one-dimensional storage things. Okay, so do the practice on that, and also just dry run on these course problem, and then practice at least 10-15 problem. Okay, so these are the content of Week-9. Yeah, so in this for the exam purpose, just for uh, remember this inductive structure for this LCS, LCW, minimum edit distance. These are important. Okay, any query, anyone? All topics are now done from Week-9. If you have any query, you can ask. No query? Okay.
Sir, could you please share this PDF?
This is already there in the GitHub notes. This is the same page actually. You can see this PDS notes, na? All are there here. Okay.
Okay, sir.
So yeah, you can just see the lecture video also. You will get more clear idea on the same line. So okay, so that's it from my side. If you have any query, you can ask. Otherwise, we can close the session. Okay. Okay, then thanks everyone.
Thank you, sir.
Thank you.